Chapter 2, Part 3, Factors Affecting Acidity. What contributes to the acidity of a compound? We can analyze the structure of a compound to determine whether or not it is likely to be acidic and also determine its relative acidity compared to other compounds in a series. There are 4 factors that we're going to discuss. The first factor is electronegativity. Number 2 is the atomic radius and delocalization of charge in A-. Remember, A- is our stand-in for any generic conjugate base. Number 3 is the resonance effect, and number 4 is the inductive effect. Now, this list is not in an order that indicates any sort of priority. Rather, it's in an order that groups like things together. So the first 2 can only be used when you're discussing a series of bi-elemental compounds. This means compounds that only contain hydrogen and one other element. Think water, ammonia, hydrochloric acid. The other 2 can be used for larger compounds, including organic molecules, which is why these 2 are going to be some of the ones that we come back to the most over the course of the semester. So, what do we mean by acidity? Simplified, we're talking about how easily a compound, we're going to use HA as our generic acid, gives up a proton. When a compound gives up a proton, the conjugate base A- is formed. The more stable the conjugate base, the more acidic the proton. So you're going to see that a lot of the factors that we discussed that we consider when we're talking about relative acidity often are factors that actually just stabilize the conjugate base. By stabilizing the conjugate base, you make it easier for the proton to leave. So let's start with electronegativity. The presence of electronegative atoms increases acidity. In bi-elemental compounds, an increase in electronegativity will correspond with an increase in acidity. So in this chart below, we have a range showing an increase in electronegativity and also an increase in acidity. So as we go across the table, we see the electronegativity values increase, and we also see the pKa's decrease. Notice that the pKa for methane is 51. Now, the way that this table is laid out, we're actually looking at a row of the periodic table from left to right. So we have, after boron, we would have carbon, nitrogen, oxygen, and then fluorine. So you can look across a row of the periodic table and say with confidence that as you go across the periodic table, you are going to see an increase in acidity. The next row of this is laid out in a way that shows you that we are talking about the pKa of 1 proton. So what's left over would be the conjugate base. The conjugate base of methane would be CH3 with a lone pair on the carbon and a charge on the carbon. That would be a really, really strong base because the pKa of methane is 51. So in order to take off that proton, you'd have to do some pretty interesting chemistry. The conjugate base of ammonia is H2N with a negative charge and a lone pair on nitrogen. That's also going to be a very strong base since the pKa of ammonia is 38 to begin with. As we get to water, you can see that the pKa has gone down significantly. So water is quite a bit more acidic than ammonia. We know that the conjugate base of water is hydroxide, and hydroxide is a good base, but it's not going to be as strong as H2N minus or H3C minus. And then lastly, the conjugate base of hydrofluoric acid is fluoride. Now, hydrofluoric acid is not one of our strong acids, and yet fluoride is not a particularly impressive base, even though this is moving more on the side of acidic compared to water, ammonia, and methane. Fluoride is still a fairly weak base. Now, this next trend does something kind of opposite of our previous trend. So in our previous trend, we saw that moving across a period or across a row of the periodic table, we would see an increase in acidity as electronegativity increases. But acidity also increases as atomic radius increases, and atomic radius increases going down a group. So we'll see that acidity increases with size. So hydroiodic acid is more acidic than HBr, which is more acidic than HCl, which is more acidic than HF. However, we know that fluoride is the most electronegative element. So even though it is more electronegative than iodine, it's still not going to be associated with as strong of an acid as hydroiodic acid because iodine is such a large atom. This trend is in direct opposition with the trend of electronegativity. So you may be wondering why acidity increases with size. Let's draw some images here. So if we are looking at hydrofluoric acid, we have a teeny tiny hydrogen atom, and we have fluorine, which is bigger, but not a lot bigger because fluorine is still a pretty small element. If we were to remove the hydrogen to leave behind F minus, F minus would be a little bigger than fluorine itself when it's part of a compound. So F minus has one additional electron that's going to contribute to the electron cloud. This negative charge is spread equally across this surface, right? One negative charge spread equally across the entire surface area of the fluoride atom. Let's take a look at hydroiodic acid. Teeny tiny hydrogen. Now iodine is quite a large atom. We're down the group, right, down the column, and this is a pretty big atom. When this loses its proton, we're going to make I minus, which is even larger, and this negative charge is spread out over this massive surface area. This is kind of like the idea of resonance, where if you are able to share the charge, you're going to be stabilized. This is the idea of having a teeny tiny focused negative charge versus a very big fluffy negative charge. The big fluffy negative charge is going to be more stable. The other thing is the big fluffy negative charge is not going to be as interesting to a teeny tiny H+ as, say, our teeny tiny F-. I don't know why my H+ got so big. It would definitely be smaller than hydrogen to begin with, but I needed to include my plus charge. Anyway, so fluoride is going to be very interested in reconnecting with H+. So these two are going to be very, very attracted to each other. Whereas this H+ has almost no attraction to this negative charge that's nicely spread out over this giant surface area. So these two are unlikely to find each other again once they're separated. So let's take a look at those trends again while following along the periodic table. You can use the trend of electronegativity to compare atoms that are all in the same period. So we can compare bi-elemental compounds going across this period pretty easily. You could also make a pretty safe bet of, comparing something with silicone to oxygen because their distance across the group or across the period, and also the fact that they're in different periods but still kind of close together, means that their electronegativities are probably pretty different. So you could probably safely make that call. But typically this rule is used to just go across a period. Now our other rule takes us down a group. So acidity increases as you work your way down a group. So these rules are in opposition with each other. Another thing that you could do is you could pretty safely make some assumptions going this way, right, across a period and then down a group that's all the way on the right-hand side. So you could do that as well. So let's talk about the factors that affect acidity in larger molecules. This first one is the resonance effect. Now, if acidity is all about stabilizing that conjugate base, we've already talked about why resonance is a stabilizing force. So let's look at how that affects acidity. Resonance delocalizes the charge in the conjugate base. Remember, more stable conjugate base equals stronger acid. So let's look at ethanol as an example. If we were to lose this proton, we would be left with ethoxide as our conjugate base. The pKa of this proton is 15.9. Let's look at another example. This molecule also has 2 carbons and has a similar OH group, but it also happens to be a carboxylic acid, meaning it has this other double bonded oxygen here attached to the same carbon as the OH group. So when we lose this hydrogen, which has a pKa of 4.76, so this molecule is significantly more acidic by about a factor of 10 to the 11th. You can take the difference in the pKa's, which is about 11, and raise 10 to the power of that to determine the difference. We end up with the conjugate base of acetate. Now, acetate has a resonance form that ethoxide does not. Ethoxide has no resonance forms. Once you put that negative charge on that oxygen, it is stuck there. However, acetate can take one of these lone pairs and use it to make a new double bond between the oxygen and the carbon. And then we can take these pi electrons and push them up onto the oxygen. That gives us a resonance form. The existence of this resonance form is a stabilizing factor, so this compound is much more stable and exists more comfortably than ethoxide. Ethoxide is a significantly stronger base, whereas acetate is on the weaker side. Okay, our last factor affecting acidity in some of these larger organic molecules is the inductive effect. I have 2 definitions. This is the fancy one. Polarization of electron density transmitted through covalent bonds by a nearby atom of higher electronegativity. My simpler definition is the withdrawal of electron density from the HA bond. Now, these definitions work together. They both say things that the other one doesn't say as clearly. You do have to have an electronegative atom in order to see any sort of significant acidity, because there has to be a dipole in a molecule in order for acidity to occur. So for example, when we're looking at acetic acid, there is a dipole across this molecule because both of these oxygens are significantly more electronegative than the carbons that are on the other side of the molecule. There's also a small dipole here between the oxygen and the hydrogen, so that the oxygen is partially negative and that hydrogen is going to be partially positive. That is what makes that hydrogen a little more interesting to a nearby base. Now, what this is talking about is we want to withdraw electron density from this bond, because the less electron dense that bond is, the less secure that attachment of the hydrogen atom. So if we take electron density away from that bond, that hydrogen atom is going to come off much more easily. So in acetic acid, we do kind of have the inductive effect going. It's what contributes to the existing acidity of acetic acid. But if we add on another electronegative atom, we start affecting the direction of the dipole. Now, we still have these 2 electronegative atoms, so the dipole is not fully flipped. It's not just flat out pointing towards fluorine. but it is starting to be less significant. And that means that the electron density of this bond is going down, and that hydrogen has less holding it to this oxygen, as this oxygen becomes less electron dense. So notice the effect that has on pKa. This is only 2 pKa points, a little more than 2, but remember pKa is on a logarithmic scale. So this is a difference of 10 to the 2.2. And that's a bit more significant. That's somewhere between 100 and 1,000. Now, once we've added on 2 fluorines, we have 2 fluorines here. Fluorine is significantly more electronegative than oxygen. This dipole is no longer pointing towards the oxygens. It's pointing towards the fluorines. So the electron density is starting to live on this side of the molecule and not so much here, which means this bond is getting weaker and weaker and weaker. So we see an increase in acidity, where the pK is now 1.34. In our last example here, we now have 3 fluorines on this carbon, right? We've replaced every hydrogen that was originally on acetic acid with a fluorine at this point. All 3 of these fluorine atoms are electronegative. This dipole is fully pointing over here. The electron density of this bond is just dwindling away. And now our pKa is 0.23. This is a much, much stronger acid than what we started off with. And that is the inductive effect.